Okay, here we go. Note taking a little bit longer. All right. So, what were we doing? What's gonna happen? Who's gonna move? Let's do a little bit of review, just a smidge. We introduced probability, or the probability chapter. Like I said, it gets confusing because we're going to talk about probability throughout the term. What's the probability of this? What's the probability of that? But not in the sense that we're solving problems in this chapter. So this is a special probability chapter, and then we leave that alone. So some things that we established is just the first rule of probabilities is that the total probability of all possible outcomes must be 1. That's a fact, right? If you've taken into account all possible things that can happen, then the total probability must be 1. Right? So the total probability, of all possible outcomes must be 1. How we denote that? Whoa, they changed. I'm so thrown off, you guys. This looks so different. Anyways, I'll survive. I'll persevere. How we denote that, right, is the probability of capital S is 1, where remember, S is the sample space, where S is the sample space. And the sample space was just the list of, or the set of all possible outcomes. The set of all possible outcomes. Sounds like someone is knocking. Hey, I'm allowed to talk in here. Second thing we established, well, there were many things leading up to it, but what we were working towards was that, okay, well, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Well, the probability of A and B is the overlap, right? Where A and B are happening together. Right? And so you need to subtract that once, otherwise it's being taken into account in the probability of A and the probability of B. So for me, I always visualize it as I just take my hand, probability of A, probability of B. I need to subtract this overlap to kind of even it out, and then I can find that probability, right? Without double counting. Okay. We said, okay, there's a special case here. Right? If A and B are disjoint, right, then we have a special case where they cannot happen together. That's the definition of being disjoint, right? And so if A and B are disjoint, you can also call it mutually exclusive, but I use the term disjoint, but they mean the same thing. If A and B are disjoint, the probability of A and B is 0. That's a fact. You could use that in reverse, right? If you know the probability of A and B is 0.2, right? And I ask you, are these two things disjoint? No, because the probability of them together is not 0, right? So you can use them in either direction. So if A and B are disjoint, the probability of A and B is 0, since they cannot happen at the same time. Let me just, whoa. At the same time. Well, and pretty sure we left off talking about cards and deck of cards. We talked about Venn diagrams, right? And I did post those assignments where you can try some of them encourage you to use a Venn diagram. You don't have to, but it's a way of organizing information, right? And in terms of the Venn diagrams, if you have 3 events, right, it gets a little bit overwhelming, but as long as you start in the center, right, and then take away that amount that you've already written down. I think there's like a laptops, tablets, and cell phones example. Or was that on the, maybe that's on the quiz, I don't know. Anyways, it's 3 things. And so, yeah, maybe that's on the quiz, but there's one very similar on the assignment as well. Anyways, so give those a try. All right. I'll say that's the end of the review, because one thing I realized that I didn't say explicitly, but is also very important, is to remind you that probabilities are always between 0 and 1, right? So as a fact, a probability has to be between 0 and 1. So here, fact, probabilities must be between 0 and 1, making them a proportion, right? Proportions are between 0 and 1. How do we denote this? We say the probability of A must be between 0 and 1, inclusive of the endpoints, okay? Because if I tell you the probability of that happening is 0, it just means it's not going to happen, right? That's fine, that can happen. If I tell you the probability is 1, it will definitely happen, right? Or something in between, right? 0.8, 0.4, right? Something like that. So probabilities are always between 0 and 1. Yeah. So what we were assuming last day, right, when I said, okay, you flip a coin, what are we assuming? We're assuming that these probabilities are divided evenly, right? We take that total probability of 1 and we divide it by however many possible outcomes I have. Now that's not always the case, right? So today I want to introduce, start us off with just what if the probabilities are not evenly distributed? Okay. So if probabilities of a random process, I don't want to make it too wordy, but sure, of a random process, which is just something that generates something random, right? Flipping a coin, rolling a die, pulling a card, right? All those are random processes. Okay, so if probabilities of a random process are not evenly distributed, among all possible outcomes, we use a probability distribution to communicate those probabilities. We use a probability distribution. Oops. Oh boy. To communicate the probabilities. Okay, where am I going to grab this thing from? Nope. Here. Oh, I have a vague memory of there's an assignment question where you need the probability distribution for the sum of two dice. Pretty sure. And here it is. So you roll two dice to die, two dice. You can only die once. One die, two dice. Okay, got it. We know that those probabilities aren't going to be the same anymore, right? So the sum of two can only happen if I get a 1 and a 1, right? And so that's only 1 out of 36 combinations. Right? I can get a sum of 3 by getting a 1 and a 2 or a 2 and a 1, right? Yeah. 4, I can get 3 ways. Now I have to think about how to get there. 1 and a 3, 3 and a 1, 2 and a 2, total of 3. So notice how the 1 and a 1, right? Just because they're the same, we don't use them. The order doesn't matter, right? But when I have a 1 and a 3 or a 3 and a 1, those are different outcomes. Okay. And you can go through, and when you look at what's the probability of a sum of 7, well, that's the highest probability, right? Meaning that in terms of gambling, it would pay the lowest because it's most likely to happen, right? And then so how it works is just because of the sums, right? It's kind of gonna look like this, right? And so if you're on the outskirts, those would have a big payout, but they're also very unlikely to happen. Okay. So in terms of rules for probability distributions, let's just grab this. Grab this here. Wait. Oh my gosh, come on. Well, keep it on this page. All right. So the probability distribution is going to be exactly what we saw with the die, right? And so, or dice, maybe I'll grab that. Fill the space on the, why not, up here. We talked about it, so sure. All right. So what do we have? We list all the possible outcomes up top, right? And then we have the probability of each outcome underneath. Okay. So the probability distribution is a list of the possible outcomes on the top with corresponding probabilities that satisfy these 3 rules. Okay. Now, one of the questions that I'm going to ask you on the quiz is, oh, now we perk up, right? Oh, okay. I'm going to give you a probability distribution or a series of them and ask you which one is a valid probability distribution. We're going to do an example, right? But it's really important that you just memorize these rules. They're not too far off, but the outcomes listed must be disjoint, okay? Meaning that you can't have overlap in your outcomes, right? It just doesn't make sense. Each probability must be between 0 and 1. So if we look at all these probabilities, they're all between 0 and 1, right? You can make them decimals if you want to, but they'll all be between 0 and 1. And the probabilities must add to 1, right? Otherwise, it's not a valid probability distribution. Okay. So let me grab the example that I promised. Now, I have one complaint about this one, and I did not read the description ahead. Maybe they address it. Okay. So here we have 3 potential probability distributions that we're looking at. Okay. So what we want to do is Which, and maybe I'll call this an example or something. Or something. Which of the following is a valid probability distribution? So I know that they didn't have enough space, blah, blah, blah. But if we're talking about these income ranges, right? The first rule is that these things have to be disjoint. At first glance, it looks like they're not, right? Because it goes from 0 to 25,000 and then 25,000, just a little bit of overlap, right? But that's bad. It's understood though that this goes probably to 24,999 and this is 25,000. Usually we go up to 999 and then pick up at the zeros on the next level, right? And so, but they were probably just not paying attention. Rounded it, said, let's move on, right? Same thing with the 50, the 100, right? So it goes right up to, and so now, right, we assume they are disjoint. The income ranges are disjoint. But that's the kind of thing you want to keep an eye out for. I'm embarrassed to say that I almost sent a report to a client where I had done that. Almost. I didn't, I caught it, but because when I pulled the data, I was like, oh yeah, up to 25,000, let's say, right? And then 25,000 up to here. So then I was double counting. It's bad. But I didn't send it, but I did do it. So it happens, it happens. Okay. Criteria number one, let's assume it's satisfied, right? We assume the income ranges are disjoint. Hands off. Each probability must be between 0 and 1, right? So if we look at the first, I guess, probability distribution A, right? All of these are between 0 and 1, so I'm happy about that. Moving on to the next one, 0 and 1. Dun -dun. Right? As soon as I have a negative, right? So now B cannot be a probability distribution because all probabilities are not between 0 and 1. So I'll write that here. B is not a valid, I'll write probability dist, prob dist, just because I'm lazy, since not all probs are between 0 and 1. Okay. C looks fine to me, right? They're all between 0 and 1. So then the next thing I need to do is move down the list. The probabilities must total 1. And so then what I'm going to do is I'm going to calculate the total. And to save us some time, I'm going to tell us that this is 1.06 and this one is 1. I don't even bother with B because it's already been cut. Okay. So here, now, right, that's bad. So A is cut. A is not a valid probability distribution since the total is not 1. Which means that C is a valid probability distribution. Therefore, C is a valid probability distribution. Whee! So now, right, we can say that, okay, the probability of just randomly selecting someone and they have an income in between 25,000 and not 50,000, but 49,999, right, per year is 0.27, 27%. Right? And so, so now we can grab these probabilities and they're not evenly distributed, right? They're roughly even, except for this last one, right? A little bit lower. It's hard to get there. That's the worst. Don't think about it. It is the worst. Okay, so C is the valid probability distribution. Okay, and now we can use these just to find different probabilities, right? And on to the next thing. Oh, but first, let's use this. What if I asked you, what's the probability of making less than 100,000 per year? Right. So that's going to be everything except 0.16, right? So knowing that the total is 1, I can just take away 0.16 and I would get that final probability, right? Which is also going to be this plus this plus this, right? Since they are disjoint, you can just add them all up. So I'll write that down. So for example, use the probability distribution to find the probability of making less than 100,000 per year. So we said, okay, well, that's going to be this plus this plus this. And so the probability of less than 100K plus, I'll use that shorthand notation, otherwise it gets too long, is going to be the probability of 0 to 25 plus the probability. So this is the long way, 25 to 50, plus the probability of 50 to 70 or to 100, I guess. Wow, they made weird leaps here. You can add them all up since they are disjoint. So if they're disjoint, there's no overlap, so you can just add them all up. So here I'll make a note. We can add these up since they are disjoint. Yeah. And I'm going to say it's 0.84. Yeah. Or, right, what you probably did just kind of intuitively was, okay, well, I'm just going to take away the one that I don't want, right? The probability of less than 100K plus is 1 minus the probability of 100K plus. Which is 1 minus 0.16. And how can I keep this on one page? Kept it pretty cramped here, 0.84 again. Yeah. The tool that you used here, even though you don't call it anything, right? When you do the 1 minus, oh, I'm just going to take away the thing that I don't want. What you're doing is finding the complement. right? And so when we use this property, we are finding the complement and it's complement, not complement, complement. And we're really good at just kind of understanding complements. And so let's see here, the complement of an event, it's fun to say too. At least in the kind of the beginning of stats like we're doing here, we usually denote it by a superscript C, right? The complement of an event. And often I'll read it as not C or not A, right? Not A, not B. And sometimes, just as a heads up, I get lazy and I do a little A prime, which can be confusing if you're from the calculus side of things, right? Whoa, you want me to take the derivative of what? There's nothing there. Well, it's easy, it's zero. No. Right. And so sometimes I get lazy and I'll do a little prime. But for you guys, I should be doing a C, but sometimes I slip up. So just it's good to be aware. Okay? So or A prime. But I'm going to try my best to use the complement. Okay? And so the complement is just everything that's not in A, right? Complement of A. The complement of 100,000 is everything that's not in 100,000, right? All those other ones. So, it's in there, but I think it doesn't hurt to. You're going to read it as the complement of A or sometimes I just say not A. It's sloppy, but it's quicker. So what are some rules that we already have a handle on then, right? A, if I add up the probability of A and the probability of not A, then presumably I've covered everything in the sample space, everything that can possibly happen. So the sum must be 1, right? And then the probability of A, if you wanted to find it, well, that's just going to be 1 minus the probability of not A, right? And so A and not A are, of course, disjoint. Otherwise, you're not looking at not A, right? So, so that's why you're able to add these across here. Okay. Let's see here. Just some general notes before we get too deep here. There are questions that might ask you for the probability, and then there are some questions that ask you for the percentage, but this is a good time to remember that proportions, probabilities, and sort of percentages, they're all the same, right? And so it's just a matter of how you present it, right? And so let me start with probabilities. So probability is a proportion, right? Because proportions have to be between 0 and 1, which are roughly percentages. Yeah. So a question can ask for any one of these 3. The value you're finding is the same for all 3, right? But how you report it, if you're asked for a percentage, you have to multiply by 100, right? And so these, are used interchangeably. I call them the 3 Ps, right? Proportion, probability, percentage. So they're all the same. So that's my first note. My second note is whenever we're doing any math with probabilities, right, or proportions, we have to use the decimal version, right? We have to use a proportion. So any math, oops, any math we do involving probabilities should be done using proportions. Which are between 0 and 1. Right. Okay. So those are just things to remember. Okay. So I talked about the complement, we've talked about probability distributions, we've talked about a lot of things so far, disjoint. It's time to introduce independence. Yeah. And so independence is, oh, I did grab this one. I'm like, hey, this is a great description. But I don't feel like writing it out. It is in my notes, just wasn't paying attention. So, 2 processes are independent if knowing the outcome of one provides no useful information about the outcome of the other, right? And so really what it links back to is if I know that the probability that, you know, that I have had lunch already, does that affect the probability that you've had lunch? It's a bad example, right? But when knowing the outcome of one thing, I tell you, oh yeah, I had lunch already. Does that impact whether you've had lunch already? Probably not, right? We're all independent in that sense, right? And so here, so that's how we talk about independence. So knowing that one thing has happened, right, doesn't affect the outcome of another one. And so an obvious example, if I flip a coin, right, I tell you, oh yeah, I got heads, right? That does not affect the probability of getting another heads the second time, right? They're independent events. And that's how casinos make all their money, because if you see a chart and it says, oh yeah, I've been flipping heads 110 times in a row now, you think, oh yeah, I'm gonna bet on tails, right? Because the probability is very unlikely. However, because the probability is all the same, right, for each independent toss, it actually doesn't matter. It's still 50-50, right? So it's unlikely that you're gonna see that. But in theory, it's equally likely to see any combination, right? And so, and that's because they're independent. Yeah. But our brains just can't do that. So there's this phenomenon where you can easily spot if a human has, so if I ask you to randomly generate 10 numbers, right, between 0 and 10, right? You write out your list, oh yeah, so random, so random. And then, but if I went around the room, I would be able to tell you, okay, you generated this one, and then someone's using a machine to randomly generate numbers, because our brains think, oh no, it has to be random, so I can't have a 1 again, right? Oh no, I've had 3 1s already. I can't do it, right? But each value is equally likely every time, right? And so, but our brains just can't handle it. But that's the independence, right? So just keep that in mind. Okay, so flipping a coin, flipping a coin and rolling a die are two independent processes, right? And so things like stock prices are not independent, right? Because they kind of go up together and they fall together. And sure, you'll have like little stragglers that go against the grain, but in general, the market's up or the market's down, down, down. But that's okay. Still happy. Right? And so when knowing that the Apple stock went up, right? That's great. Then almost all the other stocks are also going to follow, right? So that means that they're not independent anymore. So we're going to talk about dependent events or not independent events. For some reason, I don't typically call them dependent. I call them not independent. It's weird, but I don't understand it. It's just how I was taught, I think. So we're gonna start with the special case where things are independent, and then we're gonna move to dependent events tomorrow. So we will start by considering the special case of independent events. Then move on to not independent. I'll write dependent here, just so it makes more sense, events. Probably tomorrow. But I won't commit to a date, today or tomorrow. Yeah. When we talk about, so just as a heads up, when things are not independent, that's what we call conditional probabilities, right? So conditional on A happening, what's the probability of B? Right, because now they're not independent anymore. So these, we're going to call them conditional probabilities. Now, this is where I want to point out the difference between being disjoint and independent, right? Because that's a really confusing thing that we have to deal with, okay? And so here I want to write disjoint versus independent. If we're talking about disjoint events, we're talking about the outcomes. Sorry. Oh, hello? Scared me. Oh, hello? Hello?
Yeah, I wrote something. Yeah, I wrote something on the chat.
Oh, here, I'll pull it up. I can't see the chat when I okay. Like rolling a die, flipping a yeah. Yeah, it's true. I can't see the chat. But if you, so each time that you roll a coin, or just roll a coin, well, you could roll a coin, I guess. Each time you roll a die, right? So you don't have to talk about two different processes, but it's just flipping a coin. Each time you flip a coin, it's independent. And each time you roll a die, that's also independent. But also, if you flip a coin and roll a die, those two things are independent as well. You can do all these different combinations. Does that help? Sort of. Okay, awesome. Oh, wrong one. Hey. Okay. So disjoint has to do with the outcomes, right? It means that these outcomes cannot happen. There's no overlap here. Okay? And so disjoint says that two events is when two events have no outcomes in common. Maybe I'll just highlight the outcomes because that's the emphasis, right? Is that it's on the outcomes. And what we said was, okay, I can summarize that with the probability of A and B is 0. That means that there's no outcomes in common. They can never happen at the same time. Whereas independence, now it's talking about the probabilities, right? Knowing the probability of one outcome has no impact on the probability of the next outcome. So the independence, knowing the outcome of one event does not change the probability of the next outcome. So it has to do with the probability. So that's the key difference. Highlight that. So like I said, we're going to focus on independent outcomes. And then in section 2.2, because we're still in 2.1, it's a big section, then we start talking about conditional probabilities, right? Knowing that this happened, then that's going to change the probability of the next one, right? Kind of boring example, I guess, but knowing that your roommate got COVID, all of a sudden the probability that you have COVID is now a lot higher, right, than before. I know. I feel like it was like pretty nice for a lot of people, except if you're in school, then you're just sick and you still have to do all the same stuff. I know, it's crazy. All right. Yeah. So I'm going to read through this and then we're going to go through it again and just pick it apart. Okay? So the multiplication rule for independent processes. If A and B represent events from two different and independent processes, they don't necessarily have to be different, but I guess here it says so, and independent processes, then the probability that both A and B, oh, that's why they're different. Then the probability that both A and B occur can be calculated as the product of their separate probabilities, okay? Which means that we can find the probability of A and B by taking the probability of A times the probability of B. Now that's pretty neat. Yeah? So that means that if you can argue that the A and B are independent of each other, right? Flipping a coin and rolling a die, they're two independent processes, right? They're independent of each other, but they're also independent inside, right? But now we're talking about independent of each other. So now I can take the probability of flipping a head and rolling a 2, right? Notice how I said and. I can find that probability by multiplying them, right? 0.5 times 1/6. but that was a bad. Fractions and fractions, 1/2 and 1/6, or times 1/6. Okay. In fact, we can extend it as long as you have k independent outcomes, then you can just multiply those probabilities to find the probability of them all happening together. And so, okay, how I would kind of summarize this, right, this whole blurb is, if A and B, I would just replace the rest with are independent. Just to simplify things, right? To be true, the rest has to be there, but for us, when we're reading this, right, the first time, it's a lot. So if A and B are independent, then the probability that both A and B occur can be calculated as the product of their separate probabilities. Okay, so let me summarize that down here. I'm going to rewrite that. So if A and B are independent, then the probability of A and B is the probability of A times the probability of B. Now, this is only true if they're independent. Okay? So we'll have a similar formula, not the same, but similar formula for when they're not independent. Not independent. Okay, and so here, I'll do it in red. Note, this is only true if they are independent. How I like to use this instead is not to ask you to find the probability of A and B by multiplying the probabilities, because it develops bad habits, right? Then you think, oh, I can just multiply those probabilities and find the probability of A and B. That's not the case unless they're independent, right? And so it's only true if they're independent. So how I like to make you use this formula is I give you each, you have each of these three components, right? And then you use that to argue whether A and B are independent or not, right? How would you do that? So if I give you those probabilities, right, then you can multiply the probability of A times the probability of B. If it is exactly the same as that probability of A and B that you have, then they are independent. Okay? So that's how I like to use this formula, is kind of to give you the three components and then you determine if A and B are independent. Okay. So if we know the probability of A, the probability of B and the probability of A and B. And often on a quiz, right, I'll have it so that you find the probability of A and B in one of the previous parts. You find the probability of A, probability of B. You find all those probabilities, so you'll have them from previous parts, and then I ask you if they're independent. So if we know these three things, we can use the formula to determine if A and B are independent. To determine if A and B are independent. And I'm gonna switch something up here. It's more for me than for you. If we shuffle up a deck of cards and draw one, is the event that the card is a heart independent of the event that the card is an ace? All right, so we have to have some knowledge about a deck of cards, but let's start this off by determining what my outcomes are, right? Or my outcomes. So I'm talking about a heart or an ace. So I'm gonna let H be drawing a heart. And A be drawing an ace. Now I haven't given you the probabilities, but we know these probabilities, or we can find these probabilities. So we know the probability of drawing a heart, right? We know that there are 13 out of 52 cards that are hearts. We know the probability of an ace is 4 in 52. And I know there's one ace of hearts, right? And so the probability of A and H, is 1 in 52. So I want to know, is the event that the card is a heart independent of the event that the card is an ace? So now I have these probabilities. So what I want to do is I want to use that formula. And if they are the same, then they are independent. Okay. So in general, let's just remind ourselves that if A and B are independent, the probability of A and B in general is the probability of A times the probability of B. I'm going to translate this to A and H, all right, just to kind of keep myself sorted here. The probability of an ace and a heart is the probability of an ace times the probability of a heart. You just take that generic formula and translate it to your outcomes. And what I want to know is this true, right? Do they equal each other? So I put a little question mark over my equal sign because I don't know yet. I know the probability of A and H is 1 in 52. And I still don't know if that's the same as the probability of A, which is 4 over 52 times 13 over 52. But multiplying fractions, right? You can just multiply across and then you can simplify. And with a little bit of massaging here, you get to 1 in 52, which is the same. Whee. So what we can say is we can say that since the probability of A and H is equal to the probability of A times the probability of H, we can conclude that A and H are independent events. We can conclude that A and H are independent events. One thing to note is that they have to be exactly equal. Okay? So sometimes they get very, very close, right? But they have to be exactly equal. So that's why you don't want to do any rounding, right? Because that'll mess you up. So here, they must be exactly equal, which they are in this case. Okay. So that's how we're going to use that independence formula most of the time. Right? It's just to see if things are independent. How would I make this not an independent situation? What if I said, oh yeah, I drew a heart, right? And I drew a 4 of hearts, and I did not put it back in the deck, right? Then for the next draw, right now I know I have fewer cards, and so now all of a sudden it depends on the previous card that I drew, and that's for next day, tomorrow. But that is how we would change the card situation. As soon as we're doing it without replacement, changes the probabilities. But we're still with independent events. Okay, so if I tell you that I'm right-handed, does that affect the probability that you are right-handed? No, right? Oh, all of a sudden you're like, oh, I can't even hold it with my left hand. Oh, I felt the urge to start writing with my right hand. No, that's not how it works, right? And so our handedness, let's call it, we're all independent of each other, right? Not independent of our parents, right? But if we do a random sample, then it's unlikely that you and your parents and your siblings would all be in the same sample, right? And so in general, in the population, we're all independent. So let's do this example here. Where is it? Oh, I did a little mashup. Okay. I see. Here's what we need to know. And then I'm gonna bring in the ones that I want. Okay, yeah.
Is this formula applied for variables as well?
Yes, if they are independent. So as long as they're all independent, exactly. You can just keep going and going and going and going, right? And you can just keep multiplying things if they're independent. So that's exactly what we're gonna use. So about 9% of people are left-handed. I thought it'd be higher, but who knows? So we can assume, I'll call it handedness, right-handedness, left-handedness, is independent within the population. And in this case, that's totally reasonable, right? Especially if we're selecting at random, right? And so it's kind of my mashup example. Suppose 5 people are selected at random. Okay? So when they're randomly selected, especially, then we can assume that things like whether they're right or left-handed is definitely independent of each other. Yeah.
Question.
Yes.
If we are given an assessment, will we be given the assumptions or would we make them ourselves?
If you are using the fact that they're independent and it doesn't say these things are independent, then you would need to argue it. But usually I'll say something like, these things are independent of each other. Then what happens, right? Or you'll have shown in a previous part that they are independent, right? So usually I kind of hold your hand all the way through, but yeah, because there's a lot of rules. But yeah, so I want you to argue it, but usually I've kind of forced you to argue it throughout. So you don't have to start fresh. So if we select 5 people at random, then what is the probability that all are right-handed? So here, right, if all of these are independent of each other, how I like to kind of visualize this, and maybe it makes sense, maybe it doesn't, but if I have 5 people selected at random, then I can make kind of 5 slots, 1, 2, 3, 4, 5. Person number 1, person number 2, 3, 4, 5. And then this way I'll be able to kind of visualize the scenario that I'm looking for. Sometimes it gets to be a bit much, but sometimes it's just right. And so let's see here. Here I have person number 1, 2, 3, 4, 5. So how I'm reading this is the probability that all are right-handed. There's a little bit of work we haven't done yet. So let me just scoot this down. Do you already know what the probability of being right-handed is? Yes, why? Because you took the complement. You didn't call it that probably, but you said, well, 1 minus 0.09, 0.91. Right, and so first let's establish some notation here. So I'm gonna let L represent a left-handed person. And I'm gonna let R represent a right-handed person. I also know the probability of it being a left-handed person. Remember, probabilities are between 0 and 1. Yes?
I'm sorry, but it's a little bit confusing with me because I assume that there are people both. So with this, like.
Oh, like so someone ambidextrous? Ambidextrous is when you're equally capable with both hands, basically superhuman.
No, they exist.
They do exist, but typically, one, they're very rare. So it's the same as a coin landing on its side. It can happen, but we're ignoring it. But it's also, they would be just a little bit, it's impossible to be exactly the same. Right, so they would be a little bit stronger, arguably, right, on one side, even though they're, fully functioning. Can you imagine how much I'd get done? Be like, yeah, here, but I need 2 brains too, I guess. But
so we're going to assume that the population is just divided in left-handed and right-handed.
Yeah, and we use that simplification a lot, right? With the coins, with the left hand, the right hand, right? Yes, no, maybe so, no. But we, what we'll see later is if we're able to reduce it down into 2 scenarios, it makes it a lot easier to deal with. because then we have a binomial or a binary situation. And so there are kind of tricks that we can use for that. So, yeah, it exists, but not here.
Because I just thought that in test, could you mind state it more clearer? Because like we have a lot of assumption in mind.
Yeah, I mean, this, I feel like this is very obvious because I never talk about ambidextrous, right? And so don't worry about that. Don't overthink things. Don't go making up a third scenario. If you can just, if you see two, there are only two, right? So, and if you are unsure in a quiz, then you should just ask me, right? And I'll tell you. So the probability of being left-handed is 0.09, and the probability of being right-handed, therefore, must be 1 minus 0.09, which means the probability of being right-handed is 0.91. So when I want to answer, what's the probability that all are right-handed? The scenario that I'm talking about here is 1 is right-handed, and 2 is right-handed, and 3 is right-handed, and 4 is right-handed, and 5 is right-handed. Whenever you catch yourself saying and, you're going to be multiplying. Okay? And so here, I'll use 1 and 2 and 3 and 4 and 5. So when you're saying and, you're going to be multiplying these things. Yeah. Now, you're going to put the probability, or I put the probability of each thing happening that I want to happen, right, in each of the slots. So here I would say, okay, well, I want the first one to be right-handed, and the second one to be right-handed, and the third one to be right-handed, and the fourth one, oops, 4. My brain can't handle it. All right, so 0.91 times 0.91 times 0.91. So then, right, we multiply this out, right? You can skip this part and you can just say, okay, well, it's all the same probability time to the power of 5, which is 0.624032145. So therefore, the probability that all 5 are right-handed is 0.624032145. You can use this in a lot of scenarios, right? What's the probability of flipping ahead 6 times in a row? 0.5 times 0.5 times 0.5. Is that different though from flipping ahead and then flipping a tail and then flipping ahead and flipping a tail? No, right? Because it's still 0.5 times 0.5 times 0.5. So any combination that you do is going to be 0.5 to the power of 6, assuming you're flipping 6 times, right? And so although it seems strange to us, the probability actually stays the same. What's the probability that all are left-handed? So now we do the same thing again. 1, 2, 3, 4, 5. Right, I've got 5 people. 0.09. This one's not so interesting, right? Times 0.09 times 0.09 times 0.09 times 0.09, which is just 0.09 to the power of 5. which is 0.0617174649. You could switch it up. You could say, what's the probability that the first person that you draw is left-handed and everyone else is right-handed, right? Then you would have 0.09 times 0.91 times 0.91 times 0.91 times 0.91, right? But be careful, because if I said something, so here, let's say the little subpart, what is the probability the first person is left-handed, oops. Oops, and everyone else is right-handed. 1, 2, 3, 4, 5. Oops. 0.09, 0.91, 0.91. Right, so this one's left, this one's right, 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 right. You can multiply through and find that probability, but here is where I want you to note this is not the same as this subpart. What's the probability that one person is left-handed? What is the probability one person is left-handed? Why is that not the same? Here, I'm forcing it to be the first person is left-handed, right? But if it's just one person is left-handed, it could be the first person or the second person or the third person or the sixth person. I developed 6 somehow. I don't know where I skipped. I have to watch back the recording, but I never will, right? Because, right, so whenever I'm saying or, I would have to add up all those probabilities, right? I would find each of those individual probabilities and then add them up, okay? And so here, we would need to find the 5 different scenarios and their probabilities and add them up. This is what we'll be doing in the binomial section. Okay? So we will have a way to deal with that, but we don't quite yet. Right? So it's good to kind of get in the habit of saying, okay, well, these things are different, right? First person, then I'm fixing the first person is left-handed, right? In the next one, just one of them is left-handed. I'm not deciding where, but we'll be able to find it, just not now. Not now. And then finally, what's the probability that not all of the people are right-handed, right? This is one of the ways that we're going to use the complement, right? I want to find the probability that all right people, no, all right-handed, but I want the complement of that, right? Because I want not all right-handed. So that's going to be 1 minus the probability of all right-handed. which we said was 1 minus 0.624032141, which is roughly 0.37597, because that's all I have on my page. So you've got 2 assignments from this week already, because I broke it up into little sections. So we just did part 2, defining probability part 2. So you'll be able to do both of those assignments and try them. And we'll start conditional probabilities tomorrow. If you have any questions, let me know. Otherwise, I'll see you tomorrow.
Okay, for me,
yes.
when I did it, I'm not getting the same value that you were.
Oh, maybe I mucked it up. I'll stop the recording.